And again, welcome to today's webinar, Amazon RDS for MySQL, Best Practices and Data Migration. Our presenter today is Pavan Potokuchi with Amazon Web Services. Pavan, you have the floor.
Thanks, Anna. Good morning, guys. In today's webinar, we're going to cover a few topics related to employing some of the best practices to use Amazon RDS effectively. In addition, we'll also go over some of the best practices for migrating data into Amazon RDS for MySQL. Okay, so let's dive into the topics. So the first section, we're going to talk about best practices for high availability. If you are a current user of Amazon RDS, so you are likely familiar with multi-user deployments. So this is a deployment model that allows you to create a highly available database instance using RDS. So you can simply use the management console and check a checkbox to enable it. So what happens behind the scenes is RDS creates a secondary database instance in a different availability zone. And from the application side, we recommend that you have redundancy in the application tier as well using ELB or similar technologies, so that if there is a failure in any of the components of your application architecture, so you can fail over to the healthy availability zone and resume updates to your applications. So one thing to keep in mind with respect to multi-user deployments is that the replication is physical and synchronous. So physical is important because unlike MySQL's logical replication, which is single-threaded, physical replication will be able to keep up with increasing demand on your primary instance and ensures that the replica is up to date. It's synchronous in that any commit that you're performing is transferred to the secondary database instance, and you get an acknowledgement only after the transaction is committed to both the primary and the secondary instances. So in case of a failure, whether it's at the network level or hardware level, Amazon RDS detects that failure and fails over to secondary instance in a different availability zone. So the applications need not be reconfigured. So what we do is we update the CNAME corresponding to your database instance so that the DNS record points to the secondary instance instead of the primary instance. So so that without making any changes in your application logic, you're able to resume updates to your database. And once that is done, we also ensure that you return to your pre-failure configuration mode, which means we'll have a secondary instance in different availability zone as well. So this configuration is available for MySQL, Oracle, and PostgreSQL. So one thing that I want to highlight here is our team has been working very hard to reduce the failover time. In the past, it used to take about 3 to 5 minutes. And through end of last year, this time, the failover time has reduced drastically to less than 2 minutes. In a lot of cases, it actually ends up being less than a minute. So another deployment mode that we offer to get higher availability is read replicas. So read replicas, as you might know, use MySQL's native asynchronous replication technology to propagate writes to a different database instance. So you can create multiple read replicas as well for a given master instance, and you can make changes at your application level to serve the eventually consistent reads or your read traffic through the read replicas and serve your write traffic through the master instance and also the strongly consistent reads. So one thing to keep in mind is when a multi-user failover is in progress, so the 2 minutes time that we talked about, your database instance, the master database instance, won't be able to serve read or write traffic. However, if you architect your application such that you serve your read traffic through the read replicas, so you can ensure that your application will remain up and serve some operations. For example, if you are an e-commerce application, if you are undergoing through multi-AZ failover, you can still serve your catalog through the read replicas so that your users are able to browse your application. However, to resume transactions and your cart updates, you'll have to wait until the failover is complete. You can also use this mechanism to serve read traffic to your users when you're upgrading your instances. So you can upgrade your master instance from, say, an M1 small to an M24 XL, and for a multi-AZ instance, while this is in progress, you'll have some downtime related to failover, and during that time frame, you can serve your read traffic through the read replicas. You can also upgrade your read replicas in response to increase the demand of read. Another interesting feature that we have launched in the recent past is the ability to create replica of replicas. So this is a simple configuration with a multi-AZ instance and two read replicas. And why you would want to use replica of replicas is if you want to perform schema changes, for example, adding a column or rebuilding an index, etc. So you can test some of these configuration changes on your read replicas by turning them into a read-write instance. And you can create new replicas of that replica, and you can perform a logical failover once you're satisfied with your results, and make the read replica and promote your read replica, the first level read replica, to a master. And you do have your read replicas already under it, so you kind of get back to your previous configuration. And what more, you can also turn your primary instance that has been just promoted to multi-AZ instance for higher availability. So some of the things to keep in mind when you're using read replicas is that MySQL replication, as we talked about, is single-threaded, so it can get slow. So if you have a lot of transactions that are occurring on the primary instance, it's possible that your replica can lag. And with MySQL 5.1 and 5.5, replication may actually stop after a failover is performed. So a failover entails crash recovery of the secondary instance. And because of the way binary log works in MySQL 5.1 and 5.5, there is a strong likelihood that your replication could stop. So it's possible to skip the transaction that is running into issues and using the stored procedure here, RDS next master log. However, this could entail you losing some data on the read replicas. If that is acceptable, so that is one way of skipping through the errored transactions and proceed further. With MySQL 5.6, however, so we have a functionality called crash safe slaves that makes read replicas a lot more resilient to failures like the one example above. So with MySQL 5.6, we have made sync bin log as 1, so which removes the risk of the previously described issues. This, however, comes with some performance impact, but given the substantial increase in replica reliability, it is something that we strongly recommend our customers to consider when using read replicas. So now we'll look at some of the best practices for disaster recovery with RDS. So given all the functionality with multi-AZ deployments, with read replicas, logical read replicas, read replica failovers, so you might wonder whether you still need backup and restore functionality. So the answer is a strong yes. Replication provides you with a lot of functionality, provides you with high availability, etc. But however, if you run a delete star without a where statement, so you're going to lose all your data, and that statements get propagated to your replicas. so which essentially means unless you have backups turned on, you won't be able to recover from these errors. So what RDS does with backups is, apart from backing up your database instances through snapshots on a daily basis during your backup window, we also back up your transaction logs every 5 minutes to S3. And S3 has 11 nines of, is designed for 11 nines of durability, so which essentially gives you, with RDS, it kind of gives you very high data durability. So here is an example of an instance that is backed up along with the transaction logs. So the transaction logs can be backed up to a maximum of 35 days. If you do want to create backups and retain them for a period a lot longer than that for compliance or policy reasons, you can take backups of your instances to snapshots. For example, here, so this is a backup, monthly backup that is taken at the end of the month. So you can take that snapshot at the end of each month and then retain it for as long as you want. So the database backups in conjunction with log backups allow us to provide what we call as point-in-time recovery functionality. So you can use this functionality to say, hey, take my database, or create a database instance as it were 30 days ago, and at this point in time in the day. And what we do is we create a new instance using the last available backup and then roll forward all the transaction logs to that point in time that you've specified. Another interesting functionality related to disaster recovery is the ability to copy database snapshots across AWS regions. So as we talked about just now, you can take daily snapshots of your database instance using RDS snapshot functionality, and then you can copy it to a different AWS region. For example, you could be in the US East region and you could copy your backups to US West region. And so there are a couple of use cases. One of the use cases where you might want to do this is for disaster recovery. So in case a disaster such as a natural calamity affects an entire AWS region, you can use this functionality for business continuity. In addition, if you do want to migrate across regions, this is a functionality that will help you do that. Once a snapshot or a backup is copied to a different AWS region, you can use it like any other backup to create new instances from it in the new region. A related functionality is the ability to create cross-region read replicas. So in addition to migrating or copying backups from one region to another, you can use cross-region read replicas to create a replica of your master instance in a different AWS region. For example, let's take the same US East and US West regions. So here is, in the US East region, we have a master instance and then a read replica. You don't necessarily need to have a read replica in the same region for this functionality, but most of our customers use this particular configuration. So you can create a read replica of your master instance in US West region, as I just described, and the migration or the data syncing that happens between these regions through read replicas happens through a secure channel. And you can actually go ahead and create replicas of your read replica in a different region as well. So if a disaster affects an entire AWS region, you can promote your read replica in a different region as a master, and continue with your previous configuration for business continuity. Of course, the assumption here is you're also doing the same thing at your application level, so that you can resume operations quickly in a different AWS region. So one of the other use cases, apart from disaster recovery for cross-region read replicas, is that if you want to reduce the read latency for your users in a different AWS region, for example, the e-commerce application that we talked about. If you have a lot of users in the West Coast, you might want to serve the catalog through a read replica in the West Coast so that your users get a faster browsing experience. Okay, so after high availability and disaster recovery, let's talk about best practices for achieving high performance on Amazon RDS. So provisioned IOPS is a flagship functionality that allows you to achieve very high levels of performance using RDS. So if you are close to databases, as most of you likely are, so you know that I/O is an extremely important component for database performance. So provisioned IOPS allows you to get fast and consistent I/O performance. So here is a benchmark that one of my colleagues performed, comparing the TPS, transactions per second, for a benchmark across standard storage, which is referred to as regular here, and 2 provisioned IOPS instances. So as you can see in the blue line at the bottom, the performance of the standard storage instance is very variable. The performance of the instance with 1,000 provisioned IOPS is very consistent, but it's kind of close to the performance that you're able to get with standard storage. The instance with 3,000 IOPS performs substantially better. It's very consistent. It performs almost twice as many transactions per second as the provisioned IOPS instance with 1,000 PIOPS. So let's understand how does the latency profile looks like across these benchmarks. So here is a chart that displays the latency profile, categorizing it into 3 different buckets. So there are transactions that fall into the 3 to 20 millisecond bucket. There are the transactions that fall into 20 to 500 milliseconds, and then transactions that fall into greater than 500 millisecond bucket. So a lot of transactions are executed in less than 3 milliseconds. They are not displayed in this chart. So for the most part, if your transaction is taking less than 3 milliseconds, so your applications should be pretty happy. So 3 to 20 milliseconds is a reasonable latency target. 20 to 500 milliseconds is where you might end up with somewhat of a suboptimal experience for your users. Greater than 500 milliseconds is essentially pretty bad experience for users. So in this particular chart, you can see that the standard storage and the provisioned IOPS storage performs roughly, gives you roughly equivalent latency for a percentage of transactions in the 3 to 20 millisecond bucket. When it comes to higher latencies, you can see that provisioned IOPS performs substantially better. So the performance is very consistent, not as variable as a standard instance. Especially in the greater than 500 millisecond bucket, you don't see any transactions corresponding to standard storage. You do, however, have a percentage of transactions for standard storage that fall into this bucket. So this is a benchmark, of course, which is essentially pushing the instance, each of these instances, pretty hard. So in the real world, it's likely that you'll fall, your TPS target is much lesser than what we have attempted here with the benchmark. So let's say your target is 5,000 transactions per second. So let's see how the latency profile looks like with this. So there's a substantial change in the picture compared to what you have seen before. So this provisioned IOPS instances perform a lot better, whereas the standard storage instances, perform roughly the same or somewhat worse. So this kind of tells you that the standard storage instances have a built-in level of variability. No matter whether you're pushing the instances very hard or not, you do have some built-in variability that impacts the experience for your users. Whereas with provisioned IOPS, it's extremely consistent. Okay, so let's take the example of an instance with even higher provisioned IOPS. So we've looked at an instance with 3,000 provisioned IOPS. So this takes example of an instance with 10,000 provisioned IOPS. So here you see that the overall performance in terms of TPS, roughly twice as much as the instance with 1,000 IOPS, even though 3,000 IOPS, even though you increased the IOPS by more than 3 times. So let's understand why that is the case. So we're here, some of metrics that we dug into kind of show more light on why that happened. So you can see that the CPU performance is at 80%, which is reasonable. You're not pushing the instance that hard. Whereas the read IOPS performance stagnated at around 6,000, even though you've provisioned 10,000 IOPS for that instance. So here you can see the read throughput. So it's kind of hovering around 1,000 Mbps, or 100 megabytes per second. So this is the limit of the instance this is the bandwidth limit of a communication between the RDS instance and EBS. So each of the instances of RDS offer different levels of bandwidth towards EBS. So we're going to talk a little bit more about that. But this is something to keep in mind, the channel bandwidth limitations. Okay, so just summing up some of the discussions that we've had so far, you have multiple levers, knobs to control the performance of your RDS instances. You have your DB instance class and a variety of database instances ranging from 1 gig of RAM to 244 gigs. You can vertically scale up to improve performance. And then another knob that you have is IOPS. So you can scale your IOPS up or down depending upon your requirements. You can go anywhere between 1,000 to 30,000 IOPS. And along with these two knobs, the thing to keep in mind is the throughput knob, which we just discussed in terms of channel bandwidth. So we have a variety of instances ranging from 500 Mbps to 1 Gbps in terms of available bandwidth to EBS. And and that dictates the amount of the number of IOPS that you'll actually be able to realize. And CR1 8x large is our mammoth largest instance. It offers, while it's not EBS optimized, it has 10 gig network, which gives you better performance than, for example, an M2 4x large instance. And another thing to keep in mind is the database engine that you're using. So we have so far centered this discussion around MySQL, which has a block size of 16K. Engines such as Oracle and PostgreSQL have a block size of 8K. So that translates into higher IOPS for those engines. Okay, so let's look at the various instance types, in this particular benchmark, and take a closer look at some of these metrics. So an M1 large instance has 500 Mbps of bandwidth available to EBS. So you can see that in this benchmark, we got up to 52 megabytes per second in terms of read bandwidth. So this is kind of a cap for the M1 large instance. So M1 extra large instance, you're pushing the instance very hard, CPU maxed out at 100%, and we are able to get up to 100 plus megabytes per second. So this is the peak for this instance in terms of bandwidth. And then the M24 extra large instance has a lot more CPU available, but in terms of bandwidth, it has a similar cap of about 100 megabytes per second. So this kind of dictates the amount of read IOPS that you're able to get. So with the CR1 8x large instance, it's kind of interesting to note that the reads per second was actually 0, unlike the other instance types. So this is because for this particular benchmark, we used an instance with 130 gigs of data. And then CR1 8x large has 244 gigs of memory available. The entire database fits in the memory. So you're essentially not going to the disk for performing read transactions. And you haven't gotten as much performance boost out of a CR1 8x large instance because this is the nature of the benchmark that we have chosen. It isn't optimized as much. So you can optimize it to get to much higher performance in terms of writes per second using a CR1 8x large. So one thing that we attempted to do was instead of optimizing the benchmark, we just went ahead and created 3 new read replicas and directed most of the read traffic through those read replicas and served the write traffic through the primary instance. So this particular benchmark is an extremely read-heavy benchmark. So adding more read replicas essentially helps in terms of boosting the performance. So let's see how the overall picture looks like. So as you can see here, with the CR186 large instance with 3 M24XL read replicas, we were able to increase the transactions per second substantially from 47,000 to 126,000. Okay, so with that, I wanted to summarize some of the key things to keep in mind for provisioned IOPS. So make sure that you're using provisioned IOPS optimized instances. And so we have a range of instance types with different levels of dedicated bandwidth available to EBS. So all these are documented in our detailed pages as well. And understand the channel bandwidth limitations. So the channel bandwidth, so the channel that we have available to communicate between RDS and EBS in provisioned IOPS is full duplex, which means you have the same amount of bandwidth available for reads and writes. So 100 Mbps, megabytes per second, is the maximum available bandwidth for one of the channels. And that kind of translates into 6,000 odd 16 KB IOPS, which is what is the MySQL block size. So this is what you can aim to achieve with the MySQL instance with 1 gigabit bandwidth available for it in terms of read workload. And you can expect the same in terms of write workload. And if you have an instance with a exact 50% split between reads and writes, you'll be able to achieve twice as much performance. So 6,250 goes to 12,500 IOPS. And CR18XL, as we talked about, has 10 gigabit network. So it offers a lot more IOPS than you can get with an M24XL instance. So in our tests, we have seen we've been able to push MySQL up to 20,000 IOPS. You can achieve more depending on your workload. And one other thing to keep in mind is, even though you're not able to realize the IOPS that you've provisioned, provisioning higher IOPS could help you achieve lower latencies per transactions. And so lastly, a couple of things to keep in mind. If you're using provisioned IOPS and you're not able to realize the IOPS that you've provisioned, so there are a few things that you might want to look at. First thing is you want to see whether you're using provisioned IOPS optimized instances. If you use an M1 small or a T1 micro, the chances are you won't be able to hit the provisioned IOPS that you've chosen. The other thing to keep in mind is if you're running IO-intensive operations such as backup, snapshot, scale storage, etc., all these operations do consume some level of IO. So if you're running these operations in parallel, you'll see that your application is not able to realize the IOPS that you've provisioned. And the other thing to also keep in mind is the queue depth. So as a thumb rule, we suggest that for every 1,000 IOPS that you provision, you maintain a queue depth of 1. So this is a metric that is available in CloudWatch for you to look at. And if you're not maintaining this queue depth and your queue depth is lower, it means that you're not pushing the instance as much, and your application load is probably not as high as you anticipated it to be. And if the queue depth is higher than this metric, so it likely means that you might need to add more IOPS to your instance. And the last thing to keep in mind is, even though all these things fall in place, there are engine-specific limitations that are workload dependent as well. So you could end up with database contention, deadlocks, etc., that could not lead you to getting the IOPS that you provisioned. Some of the other best practices to keep in mind unrelated to provisioned IOPS is, so storage engine, we strongly encourage you to use InnoDB, which is the default storage engine with RDS MySQL. MyISAM is not transactional, so some of the functionality that we talked about in terms of backups, in terms of read replicas, etc., won't work as well with MyISAM. So we encourage you not to use it. The second thing to keep in mind is you have a variety of features available to proactively monitor your database instances. One such feature is CloudWatch alarms. So RDS exposes 14 different CloudWatch metrics, including CPU utilization, memory, storage utilization, etc. So we encourage you to set alarms on these metrics so that you can proactively engage and address issues such as, hey, my instance is running out of storage, so you can perform a scale storage operation and response proactively. So adding these alarms is important. The other thing that we have added in terms of functionality is SMS and email notifications to key database events. For example, if your database instance is undergoing a failover, subscribing to failover-specific notifications will allow you to get alerted about it. And lastly, keep in mind that you don't want to create substantially large number of tables using RDS MySQL, because that slows down crash recovery process, which also impacts the time it takes for failover. So if you have 1 million tables, the chances are your failover will take substantially longer than 2 minutes. Okay, so let's talk a little bit about data migration practices. So if you are having a new application or if you are having an existing application on premises or on EC2 and you want to move data to RDS MySQL, so we're going to talk about a few best practices and procedures to do that. So in terms of pre-migration steps, so we have a document that part of our user guide. We encourage you to take a look at it. So in terms of pre-migration steps, you want to take a snapshot of your database instance created on RDS. You want to disable backups because you don't want backups associated with the bulk load of data. You can also consider using single AZ instances, as part of data loading. So let's talk about the overall process. So you can break the import process to RDS into two big buckets. The first bucket is taking a backup of your on-premises instance. So you would want to do this typically on a read replica or a slave of your master database instance on-premises. MySQL dump is a very intrusive process, and doing it on a slave is advisable. And so taking a backup and setting up the initial baseline is the first step. So you can take the backup file, put it in the staging area, and we encourage you to consider transferring these files, the backup file, to staging server on AWS. So with RDS, you cannot copy files directly as you don't have host access from a manageability perspective. So you can run the MySQL dump utility and import data remotely, but sometimes you can run into network timeouts and issues like that, and which means you might have to restart the whole process. So being able to copy these files into an AWS environment and uploading them or importing them, we think is advisable. So you can use an FTP or a UDP protocol to copy these files securely to an EC2 instance, and then run a load data in file, we're going to talk about it a little bit, or a MySQL import utility to establish the baseline. So the thing to keep in mind is, depending upon how large your data set is, this could take several hours to complete. And as you complete this first step, it's very likely that your production database instance on premises is accruing transactions and updates and writes and things like that. And so you would want to catch up your RDS instance with those transactions to ensure that you're able to cut over in as less time as possible. So you can do that by setting up replication between your on-premises instance and the RDS instance, essentially making the RDS instance as a slave to your on-premise instance. And then once that is done, you can promote your RDS instance and then point your application to it. Okay, so let's dig a little bit into the details of the steps. So here we're going to create a DB instance for MySQL using the CLI. So in this particular argument, we have set the backup retention to 3, but since we are preparing this instance for data load, you should consider setting the backup retention to 0. And you can, and then the next step is we create an EC2 instance after that for staging and copying files, etc. So the first step that we talked about. And then the next thing that you can consider doing is creating a replication user on the master so as to set up the whole replication chain for catching up the delta. And so one thing to keep in mind is you want to record the binary log coordinates for establishing the replication. So in the previous step, when I suggested that you take the backup from a read replica, one of the things that you should do is disable the replication between your master and the slave on premises before starting this process, so that your binary log coordinates are recorded appropriately, and when you set up the replication from your master, the replication resumes from that point forward. And so you can, there are several ways. So we talked about a couple of protocols to transfer your backup files from your on-premise instance to a staging server on EC2. And so there are a bunch of different ways that we have tried out in the past. And you can choose whichever is applicable for your use case. So we have had customers using AWS Storage Gateway, which is a very easy way for you to move data between your on-premise infrastructure and AWS. You could consider using that to establish the baseline, or you could simply copy the files using SCP or UDP to an EC2 instance. Another point to keep in mind is if you're using Direct Connect, this process becomes faster. And apart from that, you could also consider using a few WAN accelerator products that work with AWS. And so here are a few vendors that supply these products, and that will help you accelerate the migration time as well. Okay, so you might want to compress your backup files because of course it's just going to help you reduce the migration time. And once the files are copied, you can create a database that reflects the schema of your on-premises instance, and then you can use a local load data, local in file command, or a MySQL import utility to establish the baseline. So once that is done, you already set up the replication user on your master, you should use the RDS set external master command or stored procedure to establish the replication stream. So if you see, the last two arguments here are related to the bin log position or coordinates that we have collected in one of the previous steps. So once that is done, you can start the replication and catch up the delta. Okay, so after that replication, before the replication stream is established, you might want to stop the service or application that is pointing at the master. I'm sorry, after the replication stream is established. So this is to ensure that you don't keep collecting updates on your master instance, because as you keep collecting them, they need to be caught up with the RDS instance. So at some point, you have to pull the card and catch up all the rest of the transactions that are accrued on your master to the RDS instance. Once that is done, you can stop the replication process and point your service or application to the RDS instance. And you'd also want to do a reset external master so that the replication is terminated. So there are a few post-migration steps that you might want to look at. So we've disabled backups primarily for the bulk load process. You would want to enable backups as soon as you cut over your application to RDS. You would want to also turn on multi-AZ for high availability, and a few other things that we talked about. Make sure that you set up CloudWatch alarms to proactively monitor the health of your database instances. Also turn on key notifications to receive alerts associated with database events. Okay, so there are that about covers the data import process, And so we have a bunch of documents that are available for you, both in our detail pages as well as the user guide. And here are a few links that you can look at to learn more. And so I'm going to turn it over to Anne to start a poll.
That is great. Thank you very, very much, Pavan. Before we get into our question and answer session, we'd like to ask the audience to complete 3 poll questions for us today. First question is posted. Thank you for our first poll question. Moving on to our second poll question. Thank you again. And our final poll for today. Thank you again for answering our 3 poll questions today. We will now start the Q&A. Pavan.
So I have a few questions here that I'll start answering. So the first question we have is, once in AWS, if we choose to export our data out for any reason, is that easily supported? And a follow-up question, can we take a MySQL dump of our entire database? So let's start with the first question. Yes, you can export the data out of an RDS instance, and you can use MySQL dump for that. In addition, with MySQL 5.6, we also support replicating out of an RDS instance to an on-premise instance. So in this particular example, we talked about migrating data from an external instance to an RDS instance. With MySQL 5.6, we also support replicating the other way as well. If for any reason you want to take your data out from the RDS instance. So a lot of details around that is covered in our documentation, the links that we had in one of the slides before. Okay, so we have a second question here. We moved from MySQL to RDS M1 large instances 2 weeks ago, and then saw the new M3 large instances. What is the best practice and process to move from M1 to M3? We have one multi-AZ instance and a read replica. So that's a great question. So there are a couple of ways that you can consider moving from an M1 instance to an M3 instance. So the simplest way is in the management console, we have a modified database instance workflow. So you can go through that, just change the instance type from M1 large to M3 large, and then click apply. And so the thing to keep in mind is you can either have this change done in your maintenance window, which is the default option, or you can say apply immediately, which means the scale-up process happens immediately. So for a multi-AZ instance, the way we do this is we upgrade the secondary instance first. So your application will still be accessing your primary instance and will be up. And after that, we initiate a failover, which typically takes 2 minutes or less. And once the failover is complete, your application can start resuming operations. And we upgrade the standby instance after that to scale up. So in all, it takes a few, 2 minutes or less to complete the scaling process. One other way you can consider doing it is you can upgrade your read replica first, which you seem to have, and promote the read replica to a master, and then rename the read replica. This is a little bit roundabout, but it gives you more control in terms of the timing, etc. So you could choose either of these options to perform the upgrade. Okay, so we have a third question here. Which engine was used for benchmarks, InnoDB or MySQL? So we used InnoDB, which is the default storage engine for RDS.
Okay, Pavan, we have a few other questions here. If you could take a look at from our audience today.
Right. Okay. So what's the latency? I'm going to pick some questions from here. So what's the latency for read replicas across geographic regions? So in terms of latency, it's probably in the order of tens of milliseconds. And the other thing, because the thing to keep in mind is, of course, the transfer happens through wire, through the internet, even though we have an encrypted channel, so it isn't dedicated. Depending upon the regions that you're doing it as well. So if you're transferring data transatlantic, going from a region in US to Europe, it could take more time compared to migrating or replicating between your Northern California region to our Oregon region. Okay, so the next question is, secondary is not a read replica but a standby read-write. So that's a good question. So the secondary instance in the multi-AZ deployment mode, which is what I think you're referring to, exists in the background. It's not available for either reads or writes. It purely exists for providing higher availability. The next question we have is, what would be the effect of temporary tables on replication? So I can have Corey, one of our database engineers, touch upon this.
Temporary tables. I'm not positive, actually.
Yeah, so I think
I'd have to test it to see, because we don't always run it.
Yeah, so the temporary tables, interfere with the recovery process, etc. So we recommend that you don't use them, especially with point-in-time recovery. I for sure know that it could interfere with the point-in-time recovery process and could impact it negatively. But with read replicas, we'll have to get back. If you can pose this question on the forum, we'll be happy to respond. Is the 2 minutes for the failover AZ time or between regions? So it is between availability zones in a given region, and this is the failover time for multi-AZ deployments. We don't support synchronous replication across regions given the latency implications. And so for managing failovers between regions, it is on the the responsibility of the user to do that based on conditions that they determine are fit. Okay, the next question, can read-write replicas be kept around indefinitely? For example, for use as a reporting database where we have a full replica of the master database, but with additional roll-up tables added. Yeah, absolutely. So you can create a read replica and serve BI use cases from it. We have a lot of customers that indeed do that. And in addition, you can turn the read replica into a read-write instance and can perform aggregations and roll-ups as you see fit. But you should keep in mind that you do it in a way such that the replication stream is not compromised. So if you perform any updates and things like that on the replica, it could essentially break the replication if it interferes with the replication stream. So that is something to keep in mind. Is it possible to not reinstate a specific table from a certain point in time from a backup, not the entire database? That's right. It's only possible to reinstate an entire database, and it's not possible to reinstate a specific table at the moment. So is this cross-region failover done via CNAME, or is it a different process? So cross-region failover is not done by RDS. So it's something that has to be done from an application side. And you do have to reconfigure your applications at that point to point to the CNAME of the instance in a different availability zone, different region. PIOPS storage. What are the guidelines for recommendations, and what are some of the financial cost variants? So provisional IOPS in the US East region costs costs 10 cents per IO per month. So for example, if you're provisioning 1,000 IOPS, which is the minimum that you can choose on RDS, that costs you about $100 per month from an IO perspective. Storage has a different dimension, but the storage pricing is very close to the standard storage pricing. Okay, so we have time for one more question. When you promote a read replica to primary, is that a CNAME change similar to multi-AZ failover, or would that require an application update? So, the promotion of read replica is something that has to be initiated from the customer end. However, we have the ability to rename instances. So once you promote read replica, it's possible to rename the instance with to the same name as your primary instance. Of course, there shouldn't be a namespace collision. You might have to rename the older instance to something else or delete it. After that, you should be able to rename your read replica to the exact same CNAME. As long as the DB instance identifier is the same, you'll have the exact same CNAME so that you don't have to update your applications or reconfigure them.
Very good. I'd like to extend a special thanks to all the attendees and Pavan, our presenter today. If you have any comments on our previous and upcoming webinars or suggestions on the topics you wish AWS should cover in future webinars, please feel free to email AWS-